Welcome back to the Deep Dive. Today we're going to shortcut your learning curve by plunging into a massive stack of source material, all designed to give you the essential knowledge you need, and fast. So if you spent any time at all working with data, you know the default tools are, well, arrays and vectors.
They're fundamental, yeah.
They are, but they have this one massive limitation. They're linear. They rely solely on these fixed, kind of boring integer indices, 0, 1, 2, 3. You have to know the index to get the data.
Right, which isn't always how we think about data in the real world.
Exactly. I mean, what if you don't care about the index? What if you need a real lookup mechanism? Like, think about looking up a friend's phone number using their name.
Or getting an employee record with their ID number.
Yes. You need a dictionary, not just a simple list.
Yeah.
So, okay, let's unpack this. We are diving deep into the world of C++ associative containers, and we're focusing on the std.map. Our mission today is to figure out exactly what these maps are, how they get so ridiculously fast, and, where they can turn messy, slow code into something efficient and scalable.
That dictionary or phone book analogy it's perfect, really. A map is all about associating data based on a meaningful identifier, not just some arbitrary number.
So it's about connecting one piece of data to another.
Exactly. It maps one data type, which we call the key, to another data type, the value.
Okay, so let's get into the definition, but make it practical. When we say a standard C++ map, what are we really talking about?
We're talking about an associative container that stores key-value pairs. And the most important rule is that the keys have to be unique.
You can't have two identical keys pointing to different things.
Right, and this is the critical distinction from, say, a vector. The standard map is automatically sorted based on those keys.
Automatically. So it keeps itself perfectly ordered all the time.
All the time, which is a fantastic feature if you need ordered output, like for a report or an alphabetical list.
But wait a minute. If the container is constantly sorting itself, and you could have millions of entries, and you're inserting new ones, doesn't that create a huge performance bottleneck?
You'd think so. That seems like it would be a massive computational burden.
It does.
But that's where the engineering brilliance comes in. The map isn't just a list that gets shuffled around. Internally, it's implemented using this really sophisticated data structure called a red-black tree.
A red-black tree. Okay, that sounds like something out of a fantasy novel. What does that actually do for us?
Well, it's a special kind of self-balancing binary search tree. So when you insert a new element, the tree intelligently performs these tiny rotations and color changes to maintain its balance and its order.
So it's not resorting the whole thing, just making small adjustments.
Exactly. And that sophisticated organization is why the complexity of all the key operations, searching, inserting, removing, is described as dollars.
Okay, for those of us who haven't touched an algorithms textbook recently,
Yeah.
dollar log $2 just sounds like math. Can you give us that memorable aha fact from the sources that translates that into real-world speed?
Absolutely. This is the killer detail to remember. Think about the scale. An array with 4 billion items. Finding one thing would take, on average, 2 billion steps.
Right.
But with a map, because of that logarithmic structure, if you had about 4 billion key-value pairs, finding, inserting, or removing any single one of them would take approximately 32 iterations.
32.
32 operations.
32 steps to search 4 billion items.
Yeah.
That is genuinely incredible. It means the speed is super predictable and it's almost independent of the scale.
Precisely. And predictable performance is often way more valuable than just raw speed, especially when you're working at that kind of scale.
Okay, so we've sold the speed. Let's talk mechanics. For any developer listening, you need to include the map header file, declare your object. But how do we actually interact with it?
We've established that you use the key, not an index. But the sources point out two really distinct ways to grab an element, and they have very different side effects.
Right. This is where you have to make a smart programming decision.
It is. The first method is at the key. This is your safe lookup. If the key exists, you get the value. If the key doesn't exist,
It tells you.
it tells you very clearly. The program throws an exception. It's got bounds checking to protect you from errors.
And the second method,
Yeah.
this is the powerful but potentially tricky one, the operator key.
Correct. The bracket operator. It does two things. If the key is there, it just accesses the value, same as at key.
Yeah.
But, and here's the catch, if the key doesn't exist, it doesn't throw an error.
What does it do?
It automatically inserts a new key value pair, and it initializes the value to its default. So 0, or an empty string, or null.
Ah, so you could accidentally pollute your map if you just mistype a key during a lookup.
You absolutely can.
You think you're just reading data, but you're actually writing it? That's a huge gotcha.
It's a huge gotcha. I mean, it's super convenient for building a map on the fly, like if you're counting word frequencies, but it's dangerous if you just want to do a read-only lookup.
Okay, speaking of building it dynamically, what if you insert something and the key is already there? We said keys have to be unique.
It handles that gracefully. It just replaces the existing value with the new one you provided, so it's more like an update.
It updates the record. And if it's a new key,
The red-black tree just finds the mathematically correct sorted spot for it and slots it in. It maintains that perfect order.
that's incredibly versatile. And like other containers, you've got your basic management functions, right?
Size.
And empty,
Yeah.
size for the pair count, empty to check if it's, well, empty. And clear to wipe the whole thing.
Got it.
One little technical detail, though. You can compare two maps with or EGA. It checks them element by element.
Lexicographically.
Right, but you can't do like math operations on the map as a whole or use count to just print the whole thing out. It's too complex for that. That makes sense. It's a structure, not a variable. Okay, let's talk about using that sorted order. A lot of the time, you need to walk through all the data, maybe to print a report.
And since it's an ordered structure, traversal is really straightforward. You just use iterators, same as with a string or a vector. But what the iterator points to is unique.
Can you elaborate on that? What's unique about its structure?
Well, think of it like a special kind of pointer. It doesn't just point to one thing. It points to the whole key-value pair.
So you get both at once.
Exactly. You access the key using the identifier first, and you get the value using the identifier second. So as you move the iterator, you're moving to the next key in alphabetical order with its value right there.
That's a crucial detail. So if I'm looping through, say, a map of letters and their counts, I'd be looking at iterator first for the letter and iterator second for the count.
Precisely. And for standard forward traversal, you use begin and end. If you need reverse sorted output, you just flip it and use begin and rend.
Okay, let's shift to searching. Sometimes you don't want to walk the whole map. You just need a quick check.
Yeah.
Does this thing even exist?
Right. What's the most efficient way to do that?
Yeah.
You've got two main lookup functions. The simplest is count key. Since keys are unique in a standard map, it just returns 1 if it's found and 0 if it's not. It's a very clean Boolean check.
1 or 0.
Yes.
Simple.
Yeah.
And the other one is find key.
Right. And find key returns an iterator. If the key is found, that iterator points right to the element. If it's not found, it returns the special end iterator.
And that's often better, right? Because if you find it, you've already got the pointer to the data.
Exactly. You're ready to modify it or retrieve it, all in that $1 log2 operation.
Now let's connect this to real-world performance, especially in big applications. If you have a map with millions of customer records, you definitely don't want to be copying that whole red-black tree every time you call a function.
Oh, that would be performance suicide. You hit the nail on the head. Best practice is to pass these objects by reference.
So you're just giving the function a pointer to the original map. No deep copy.
No deep copy of all that data. And what if the function's job is purely read-only? Like, it just needs to verify a user's status.
It shouldn't be able to modify the map at all.
Then you use the gold standard, pass by const reference. You get the speed of passing by reference, plus a compiler-level guarantee that your data can't be modified. It's safe and fast.
Okay, that clarifies passing to a function. But what about the other way? If a function needs to create and return a new map, I always thought returning a big object by value was a bad idea.
Historically, it was. It meant a really slow, laborious copy process. But with modern C++, say C++17 and later, this isn't really a major concern anymore.
Why not?
Techniques like RVO, that's return value optimization, and move semantics, let the compiler basically bypass or streamline that copy.
So the data isn't physically copied, it's just moved.
Correct. The ownership of the data structure is efficiently moved to the destination variable without that exhaustive element-by-element copy. So today, the recommendation is usually just to return by value. It makes the code clearer, and you can trust the compiler to optimize it.
That's great context. So we've covered this standard sorted map, but let's go back to that idea of speed. What if you realize that, 99% of the time, you don't actually need a sorted list?
What if you're willing to trade that organization for just pure, raw lookup velocity?
Exactly.
Well, that's when we bring in the speed daemon, the std.unordered map.
The speed daemon. I like it.
It's still a container of unique key-value pairs, but the critical difference is the elements are not sorted. You lose the alphabetical order, but you gain a ton of speed.
So how does it organize the data if it's not a sorting tree?
It uses hashing. Every key you insert is run through a hash function, which generates a unique numerical hash value. That hash value tells the map which internal storage location, which bucket, to put the key value pair into.
So if I ask for a key, the system doesn't traverse a tree. It just calculates the hash, jumps directly to that bucket, and grabs the item.
Precisely. It's like a giant electronic filing cabinet where every folder has a unique number. It completely bypasses that logarithmic search time.
And the performance impact of that must be huge.
Oh, it's massive. While the sorted map gives you that great log2 umbrel efficiency, the unordered map gets you an average time complexity of unordered dollars.
Just in time.
Constant time for lookup, insertion, and deletion.
So that means if the map grows from 10 items to 10 billion items, the average time to find one thing, it just stays the same. That's the holy grail of speed.
It really is. If order doesn't matter, the unordered map is almost always the better choice for just sheer velocity. It's a direct trade-off. Guaranteed sort order versus maximum speed.
Which brings us to the applications. The so what? These things aren't just technical curiosities. They solve real, frustrating programming problems.
They absolutely do. Let's take that bracket operator we talked about, the one that inserts automatically. One classic application is frequency analysis.
Like counting how many times each word appears in a giant document.
Exactly. You start with an empty map. The key is the word, a string, and the value is the count, an integer. As you read the document, for each word, you just do word counts current word plus and say.
And if the word is new, the map creates it and sets the count to 1 if it's already there.
It just increments the existing count instantly. No searching through a list required.
And the sources mention that to do that properly, you have to normalize your keys first, right? Make sure apple and apple are treated the same.
Absolutely. The key is the identifier. So you have to make sure your identifiers are consistent. Convert everything to lowercase, strip out punctuation, all before you try to insert it.
We also saw some really powerful examples of managing complex data. You don't have to map an ID to just a number. It could be an entire container.
Right, like that car racing scenario. Imagine you're tracking a bunch of race cars. The map key could be the cod, but the value could be a whole vector of integers.
A vector representing all of that car's recorded positions during the race.
Exactly. So the map becomes this high-speed organizer. You use the car's ID to instantly pull up all of its historical data. It lets you calculate averages or find the winner without looping over the entire data set of every single car's position.
It creates instant grouping. And then there's the classic use case, the dictionary lookup.
Of course, problems that need instantaneous substitution, mapping a foreign word to its English equivalent, or one alphabet to another. That's the quintessential map problem.
What does this all mean? We've covered a lot today. The standard std.map is this ridiculously powerful tool. It guarantees its elements are sorted by key, and it gets that efficient dollar performance from its underlying red-black trees.
And that performance is predictable, even when you're dealing with billions of items.
Right, and then we learned that if what you really need is absolute speed and you don't care about order, the unordered map uses hashing to give you even faster, average, constant time performance.
It's essentially giving you instantaneous lookups. The map family is just essential when you need to move beyond simple numerical indices to more meaningful identifiers.
We've established that when you need a dictionary, a lookup table, the map is your tool. But that biggest decision still remains, that trade-off.
That's right. So here's a final thought for you to consider. When you're architecting your next project, you're going to hit this fork in the road. You'll have to decide if that guaranteed key-based sorting, which is great for reports and sequential stuff, is worth the extra, albeit small, computational cost of no-gob.
Or if the sheer velocity of the unordered map should win out.
Exactly. How often do you really need that sorted output? And when is maximizing speed truly more valuable to the problem you're trying to solve? That's the kind of decision that separates a fast application from a truly scalable one.